Hello, everyone. Apologies, I haven't been able to join you in person for this month's meetup. I have, however, pre-recorded an episode of DSP Corner, which is the introduction to the Fourier series that I had planned for last month, and that will be coming to you soon. So I hope that that is of use to you and that you enjoy that. I've been in the process of developing a workshop with my good friends at Dynamic Cast. We're delivering two workshops in total at the Audio Developer Conference this year. They will be delivered in the morning and the afternoon of the workshop day, which will be November the 14th. That will be the Monday. The workshop that I've been most closely involved in developing is called Practical Digital Signal Processing. And the plan is that I will go over practical digital signal fundamentals and techniques, and that this will be a sort of extension of what I've started to cover in DSP Corner, but will extend this learning with more visualizations and more interactive code examples for people that join that workshop. Anna and Harriet will be delivering a second workshop in the afternoon, which will be called Practical Software Engineering. And in that workshop, they're going to be sharing some techniques used in everyday coding in order to work on large code bases and deal with code bases in a professional context. Also going to be discussing reading and analyzing code and finding entry points into complex systems. So if you're fairly new to software engineering in general, or just have some experience, that one could be really useful to join. My one in the morning, I say my one, but we'll all be involved in some way in the delivery or support of those workshops. We encourage you to apply online. If you already have a ticket to ADC, you can sign up now to join the workshop. There are spaces left in person. We did make the decision to originally first open these spaces to people that hold a diversity scholarship ticket, just to make sure that we're getting the education and information to the people that may need it more first. But we understand that the concepts we're talking about could be interesting for people of all levels of experience and walks of life. So if practical digital signal processing or practical software engineering sounds like something that would interest you or benefit you, then we invite you to join us on Monday, the 14th of November, and can't wait to meet you there. I think that's everything I've got to recap on for now. If you have any questions about the workshops, yes, they will. This is quite important. They will also be available online, and online through GatherTown, which is where online ADC attendees will be navigating the conference and attending talks. We actually don't have a limit. So we have an in-person limit, but we don't have a limit online. So we can accept many, many more attendees online if people are interested. I have been told that eventually the recordings of the workshops will be made publicly available on YouTube, but this may not be for quite a while. And we recommend, for the best and most interactive experience, that you come and experience these workshops in person. There'll also be other dynamic cast members there, especially to support you and answer your questions to make sure that you get the most out of these workshops. Right, I think that is actually everything. Thank you so much and hope to see you all soon. Take care. Hello, everyone. Welcome to what is the 5th episode of DSP Corner. Today we're going to be looking at an introduction to the Fourier series. Fourier series is one of the main ideas that underpins digital signal processing. And I'm hoping that by introducing the Fourier series, it will nicely pull together some of the ideas we've been looking at in previous episodes and give us a gateway to beginning to understand the Fourier transform, which is another very important concept and arguably the most important transform for audio developers and engineers like ourselves. The lamp I'm using here to record the video has a lovely orange glow to it, so it feels like we could be almost having a fireside chat. So that's quite nice. Let's get started. First off, I'm going to just recap on the properties of sinusoids, both in a waveform view and a geometric view. This is because in a moment I'm going to show you a video about the Fourier series, and the way it is explained in that video is imagining each signal as a vector, a rotating vector with a certain amplitude and frequency. So I thought, first things first, let's recap on the 3 variable properties that sinusoid can have and look at them in both a waveform and geometric view and make sure we understand in what way those two relate to each other. So the first property we're going to look at is amplitude. This is the property that relates perceptually to the loudness of a sound. You can see on the waveform, I've labeled the amplitude here with the black arrow. You can see that we have an amplitude of 1 as we measure the amplitude from 0 to the highest point of the signal. If we look at this from a geometric view, we can see this red vector here and think of this as our sinusoid. So in terms of the geometric view, our vector will have a certain length. Now, right now we've placed this vector in the unit circle, so it will have unit length being 1, which nicely corresponds to our waveform, which also has an amplitude of 1. The longer this vector, the higher the amplitude will be, and the shorter the vector, the lower the amplitude will be. The second property of a sinusoid we're going to look at is phase. If you saw the very first episode of DSP Corner, we saw that between a cosine and a sine wave, we have this phase shift of pi over 2, which is denoted here by the black arrow. So basically we can say that a sine wave is equal to a cosine wave with a phase shift of minus pi over 2. And this is quite nicely shown in a geometric view. If you look to the right of the screen, we can see that we've got 2 arrows, one of which is representing our blue cosine wave, and the other of which is representing our red sine wave. And we can see that a phase shift of pi over 2 corresponds to a rotation anti-clockwise around the unit circle of pi over 2 radians. or 90 degrees. So seeing it in a geometric sense actually quite nicely represents that phase shift that on our waveform we see as a horizontal shift to the right. So yes, in a waveform sense, you can think of phase or phase shift as a horizontal shift either to the left or to the right. If you're shifting to the right, you're rotating anti-clockwise around the circle. And if you shift to the left, you're rotating clockwise around the circle. Now we will generally be rotating anti-clockwise around the circle, as this is the direction of positive frequency. But we also have touched upon negative frequency before, which will be in the opposite direction, a rotation clockwise around the circle. The final property of a sinusoid we're going to recap is frequency. Now, frequency is probably the most well-known property of sinusoids. It's commonly measured in hertz, which is cycles per second. And a cycle is the point at which the sinusoid begins to repeat itself. So you can see that I've labeled one cycle, also can be called period on the waveform here. And you can see that one cycle runs between 0 and 2 pi on the waveform. So it would only make sense that when we look at it from a geometric view over here on the right of our screen, that one cycle is represented by one full rotation around our unit circle. Now, how do we, in a geometric view, represent what our frequency is in terms of hertz, like whether it's a low frequency or a high frequency? So in a geometric sense, frequency will actually be the rate at which that red vector rotates around that circle. So for a higher frequency, you would have a faster rate of rotation around that circle, and for a lower frequency, you would have a slower rate of rotation around that circle. And you'll see in the video that we're about to watch that the speed at which that vector rotates draws out the sinusoidal wave. And when it's rotating slowly, you'll be drawing out a much more long and slowly oscillating sinusoid, as you would see in a low frequency signal. And if it was oscillating very fast, you'd be drawing a signal that had lots of quick oscillations, which is a high frequency signal. Okay. So let's get introduced with the Fourier series. The man that you can see on the left-hand side of the screen here is Jean-Baptiste Joseph Fourier. Fourier was a French mathematician who invented what is now known as the Fourier series through his study of the transfer of heat. Fourier theorized that any function of a variable, whether continuous or discontinuous, can be expanded in a series of signs of multiples of the variable. To put this in simpler terms, any signal, no matter how complex, can be broken down into a series of sine waves with varying frequencies and amplitudes. Let's have a look at this video that will give us a better visual idea of Joseph Fourier's theory. And this video has one of those presenters, scientific presenters with quite an old-timey voice. and the really crackly recording with a fair amount of interference. I really like those kind of presenters' voices, but hopefully the interference won't be too distracting from the content. I hope you enjoy.
A periodic waveform is one that has a shape, which is repeated at regular intervals of time or periods. To illustrate how the Fourier series may be used to represent complex waveforms, let's first apply a single sine wave to a square wave with period t. To construct a sine wave with the same period, we draw a vector and rotate it 1 revolution per period. The vertical projection of the vector tip oscillates up and down once for each revolution of the vector. When the projection moves to the right at a uniform rate, it draws a sine wave. To estimate how well the sine wave represents the square wave, we can superimpose one on the other. The approximation is only fair. The error is about 19%. Next, we tried the same fundamental, or first harmonic, and the third harmonic. If we stop the action momentarily and add the vectors, the sum produces a waveform. Which obviously is a better representation of the square wave than was the first harmonic alone. How much better is shown by the superposition test. The error is about 1/2 as large as before. When 3 harmonics, the first, the third, and the fifth, are added, the resultant waveform is an even better representation. If we again superimpose, we find the error now down to about 7%.
Wonderful. So that was an introduction to the Fourier series. Let me just see if I can minimize this video and get back to the slides. So the simplest way we can think of what we just saw in terms of the harmonics that were mentioned in that video and the vectors that were joined tip to tail to create a new waveform is that all of those elements were just different representations of sinusoidal signals. And the simplest way we can think of this is that sines are the building blocks of sound. And if we thought about this in terms of actual building blocks, we would realize that to achieve complex structures, we'll need building blocks of multiple different shapes and sizes. And therefore, in the same way, to achieve complex sounds, we'll need to combine sinusoids of different frequencies and amplitudes. So you could see that what was happening in the video is that we combined the first, the third, and the fifth harmonic, which are 3 different sinusoidal waves, all with different frequencies and amplitudes. And what that started to give us was something that started to resemble a square wave. And we're going to see that happen in real time with a code example shortly. But before we get there, I'll just remind you of sinusoid mathematical notation, because we're going to write this out in code. So this is a continuous time sinusoid denoted by the round brackets and the independent variable t for time. You can see that our sinusoid has an amplitude denoted by the capital A. It has a frequency in hertz or cycles per second, denoted by the lowercase f. And it can also have a phase shift, which is denoted by phi here. And that will be added within the brackets of the sinusoidal function if you require your sinusoid to have a phase shift in either direction. Let's talk about a couple of familiar waves and the different harmonics that they have. So if you're someone that is a musician or has dabbled in studying music theory or even music technology, you might have heard about different familiar waveforms having either even or odd harmonics, or sometimes having both odd and even harmonics. So a sawtooth wave is such a wave that has odd and even harmonics, which means it will have all integer harmonics 1, 2, 3, 4, 5, 6, etc. And I've just put the mathematical formula for the first 3 harmonics of the sawtooth wave to illustrate what values get plugged into those sinusoids in order to achieve such a waveform. So for the first harmonic, we can see that the frequency is just itself. So we can say that it's 1 times the frequency, because it's just the whatever we choose our fundamental frequency to be. And we can see that the amplitude is divided by 1, and anything divided by 1 is itself, so there's no change to the amplitude here. What we could get rid of is just the divided by 1, and it would just be the classic sinusoidal mathematical equation that we've seen many times before. So that's our first harmonic. And to that, we want to add another sinusoid, which will be our second harmonic. And you can see that here in our second harmonic, we have multiplied the frequency by 2. We've also divided the amplitude by 2. Let's say we add another harmonic to get closer to the approximation of our sawtooth wave. For our third harmonic, we times the amplitude, we multiply the frequency by 3, and we divide the amplitude by 3. And you're starting to see a pattern emerge here that each time we add another harmonic or another sinusoidal wave, we multiply the frequency by the number of that harmonic, and we divide the amplitude by that same number. So you're getting, each time getting a higher frequency. I was going to say faster frequency, but higher frequency is more accurate. Higher frequency and a slightly lower amplitude. A square wave is one such signal that only has odd harmonics. So 1, 3, 5, 9, 11, etc. We can see here that the first harmonic of a square wave is exactly the same as the first harmonic as we had for the sawtooth wave in terms of notation. You would choose a fundamental frequency for this. and it will have exactly the same notation. It will just be a singular sine wave. The only difference here is that when we go to add another harmonic, instead of choosing the second harmonic, we'll jump straight to the third harmonic, because as we said, a square wave will only have odd harmonics. So we can see here that for our second building block of a square wave, our sine wave will have a frequency multiplied by 3 and an amplitude divided by 3. For our third building block, or sine wave, we can see that our frequency is multiplied by 5, and then our amplitude is divided by 5. So essentially, it's the same or very similar as what we saw for the Sawtooth Wave. We've just dropped those second and fourth harmonics, or we've dropped, in fact, all of the even harmonics, because to achieve this waveform, we are only interested in the odd harmonics. To show this happening in stages and visually, I've broken it down to show in red here. This was the first harmonic we spoke about at the top, and that is just one singular sine wave. We add another sine wave. It starts to approximate the square wave behind in blue a little bit better, but we're still slightly far off. So as we add more and more harmonics, we start getting a better and better and more accurate approximation of that underlying square wave. Okay, we're going to attempt to quickly do this in MATLAB, which is a mathematical programming language and has very good capabilities for visualizing waveforms and general mathematical formulas and exercises that you might want to do. So let's jump over to MATLAB and have a look. Anyway, let's start with the sine wave. So we are going to create and plot a sine wave in the MATLAB mathematical programming language. The first thing we need when we want to plot a signal is a time axis. We can create a time axis in MATLAB by creating a vector with a certain range and a certain increment. And the increment that we define is the middle value here. And you may be wondering why this increment is so small. And the reason for that is because we are using a computer to plot this signal, we cannot actually plot a continuous time signal. We can only approximate a continuous time signal. And to get as close as possible to what looks like a continuous time signal, we want to make sure that our samples are spaced very, very close together to give the approximation of a smooth sine wave. And I'll show you what I mean. First things first, let's just plot it, and I'll show you what this first chunk of code does. And all it's going to do is plot our sinusoidal wave. And you can see here that I have f equals 3, and that is our frequency labeled here. And that means that there will be 3 cycles of the sinusoid within 1 second. And you can count them here. It's 1, 2, 3. And on this axis, we have our time in seconds, and you can see that at 1 second, 3 cycles of our sine wave have elapsed. Okay, probably the most important line of our code is here. And this is our sine wave. You can see that the notation in MATLAB is very similar to that we saw in the slides. We've got 2 times pi times f times t. And the f here is the frequency and the t is our time vector. And you can see that time vector along the bottom here because we've said we want a time vector between 0 and 1. With a very small step. Now, do you remember what I said about having that small step so that we approximate a very continuous sine wave? Okay, let me show you. If we take that value a lot higher and run it again, we're going to get something that doesn't approximate a sine wave. Now this doesn't look very nice at all, and that is because we don't have a small enough increment to capture all of the samples that we would need to give us our lovely continuous sine wave. So let's add those zeros back in and get our nice smooth sine wave back. Wonderful. Okay, so now we've seen the sine wave. A lot of the code that you'll write in MATLAB is to do with plotting. So everything from here down that I've highlighted is actually code for plotting. And I've tried to label it in a way that will be quite descriptive, and I will share this code afterwards if you have access to MATLAB and you'd like to try it yourself. I will also suggest alternatives for those that don't have access to MATLAB. And you can see that we've used a function called plot, and we've passed in our time vector and our sinusoidal signal, t and x. And here I've just specified how thick I want that line to be. We've given it a title, we've labeled our axis, which is very important for other people looking at your diagrams. And we've put the grid on so we can see the values a bit more clearly. Let's move on to looking at approximating a sawtooth wave from the addition of building blocks or sine waves in the harmonic series that we just mentioned. Just uncomment this. Okay, so let's quickly read through this code. We've got again our time axis and our frequency, nothing new there. I've got a sinusoid that I've called saw because this will be our sawtooth wave. And for the first one, like I said in the first harmonic, the frequency is just multiplied by 1. So nothing special here, that will just be a normal sine wave like the one we see in our picture here. I've got another sine wave, which I've multiplied the frequency by 2 and divided the amplitude by 2. A third sine wave where I've multiplied the frequency by 3 and divided the amplitude by 3. So those are actually the first 3 harmonics of our sawtooth wave. Now what I'm going to do for you is plot them. You can see here in the plot that I've added them together. I could have done this externally and then passed it into the plot, but I just did it here to make it really clear that those are 3 different sinusoids that we're adding together to start to create an approximation of a sawtooth wave. So first things first, I'm just going to take out those other additional sinusoids that we've been adding and just run it. And what we should see, if we're lucky, yes, sinusoid just like before. So this is our first harmonic. Now I'm going to add saw to our second harmonic and run the code again. You can see that this addition of the second sinusoid has actually changed our original sinusoidal signal fairly significantly. And you can begin to see how this might, in the end, become something that resembles a sawtooth wave, because it's very slightly starting to have that sawtooth ramp down and rise in amplitude, and then ramp down and rise in amplitude and ramp down. And let's add our third one and see what happens. Just going to add our third harmonic here to the plot arguments. Let's run our code again. And we can see that there is another ripple there in the approximation of the sawtooth wave. And it's very slightly edged towards being a better representation of the sawtooth wave we know and love. So what I've done for you, just to show how we can get closer and closer to that approximation, is I've written a general function which will allow us to enter in the number of harmonics that we would like. So I'll just uncomment this here. The commented code is if we want to plot all of the different iterations of the sawtooth wave over each other. But for now, I'm going to leave that commented out and plot it at the end of our for loop so that we see the resulting wave, which will be the addition of all of those sinusoidal elements. So in num harmonics, we want to choose the amount of harmonics we're going to add. Let's first choose 3 so we can see this again, just to make sure that we have a match there. Okay, perfect. We're seeing exactly the same thing. That means we're on the right tracks and the function, or, oh, it's actually not a function. I didn't put it in a function. It is just a for loop. Yeah, it would do the same thing in a function, and we would pass in the number of harmonics, for example, and the frequency, etc. But here, what we're doing is we're iterating from 1 to number of harmonics, and we're plugging those numbers in to times the frequency and divide the amplitude, and adding them all together, and at the end we're going to plot them. So let's go up to 5, because that's quite a common one. We can see that we're getting a better and better approximation. You can see where this is heading. So let's ramp up to 21 harmonics and see what we get. I've noticed you can't go much higher than 21 because MATLAB takes its time to calculate them all. And this is looking really good. You can see an almost vertical rise of the sawtooth there before it ramps down again. And yeah, this is just for 21 harmonics. And theoretically, the Fourier series is an infinite series. So we can have infinite harmonics to get closer and closer to that absolute approximation that we're looking for. And I'm very quickly going to show you how this would work for a square wave, which we said before has both even and odd harmonics. So you can see here, oh, my apologies. I meant that it has only odd. The sawtooth has both even and odd. So one difference we've made, if I uncomment the generalized for loop that I've written down here, uncomment, there we go, is for my for loop conditions here, I've said that we want to loop from 1 to number of harmonics. We want to take a step of 2 each time because we want to miss out all our even harmonics. So that is really the only difference between approximating a sawtooth wave from sinusoids and approximating a square wave from sinusoids. Let's start off with 3 and run that. You can see that we're already starting to get something that could in the end be a square wave. Let's try 5 for this one. Again, slightly closer, you're getting more ripples there from the additional sinusoid that's been added. And if we go up to 21, we should be seeing something that becomes a bit smoother at the top of each of those, well, the top and bottom of each of those periodic square waves. Wonderful. So you can see that we're getting closer and closer to what we know and love as a square wave. And as we carry on adding more and more harmonics, each with a slightly higher frequency and a slightly lower amplitude, we're going to get closer and closer to that square wave that we're looking for. And one thing I wanted to mention as well is that creating these waves with an addition of sinusoids is essentially the idea behind additive synthesis. So if you're someone that is interested in synthesizers like me or synthesis techniques, adding 2 or more sine waves is to create a new wave is a perfect example of additive synthesis. And I hope you enjoyed that demonstration and that it gave you a little more clarity on how we build more complex signals from seemingly simple sine waves and why sine waves are so incredibly versatile, even though visually and sonically they appear quite simple. Thank you for taking the time to sit in on DSP Corner with me today. And I really look forward to catching you next time. As always, you can reach me on LinkedIn at Rachel Locke or on Twitter. My handle is at Madame Modular. Always happy to receive questions and messages from members of the community, and I look forward to seeing you next time. Bye.